to introduce the first research talk of the day. This is Xin Lyu from UC Berkeley, who will be talking about fingerprinting codes and adaptive data analysis. Yeah, so let's give a warm round of applause to Jen.
All right, so thank you for attending this talk. And the paper title was Fingerprinting Codes in Geometry Runs for Private Queries and Adaptive Data Analysis. But for this talk, I guess we'll try to skip as much of private queries as possible. Let's start by, I guess, define our model for problems. So in this talk, we'll be mainly interested in answering counting queries. So say you have a data universe, capital N, that means the type of data points you might have. And I guess one example is a popular setting people tend to look at is high-dimensional data, where each person or each data point consists of D relevant attributes. For example, let's say income, gender, location area, etc., etc. Okay, cool. And once you have the data set is just nothing more than a multi-state S consisting of any such data points from the universe. And once you have your data set, you can start to ask so-called counting queries. So a counting query is just given by predicate Q, which maps every data point to either 0 or 1. And basically, I'm asking you how many data points in your set satisfy this predicate. And we say the empirical true answer to the query is just you count how many points satisfy the predicate, and let's say you normalize things by dividing by n. And then if your data set is drawn a small sample from a very large population, which we say is D, then you can also define the population answer for this query to be what would happen if you draw random point from the population and evaluate your query. Okay, so the paper was studying two questions. First, how to count privately, which is known in the literature as private query release, and how to count adaptively, which is adaptive data analysis. And again, for this talk, I guess, we're just going to skip the first part and mainly focus on the second part, adaptive data analysis. So I guess let us define the model once again, and to be more clear, if you're on the same page. So this is the adaptive data analysis model first formalized by this seminal paper by Dorf, Feldman, Hart, Ringo, and Rolf. We just received the Text of Time Award at Stock 95, so to check it out. So here we have an unknown distribution D over the domain capital N. And the algorithm will receive NID examples from the distribution, so just call it S. And then the algorithm will interact with the adversary for a couple rounds. So we will repeat the following interaction for Q round. Every round, based on the interaction history so far, the adversary will define and send the query Q sub T to the algorithm. And the algorithm is supposed to process this query and based on its data points. And it responds with the real number A sub T, which should be alpha close additively to the population mean of this query. And I guess we say the algorithm wins the game against the adversary on this distribution if with high probability with over randomness both of the initial data points you draw, because you can, I guess, you can be unlucky with your sample. But anyway, the randomness of your data points and the randomness of the algorithm and the adversary, we design our response to be alpha accurate or alpha close to the population mean. And here we are really interested in information theoretical questions. So I guess we cannot assume any computational upper bounds on both the algorithm and the adversary side. We just ask what is the minimum number of samples required to design an algorithm that can win the game against any possible adversary and on any possible distribution. And I guess then for the purpose of worst case analysis, you can also assume the adversary actually has the knowledge of the distribution D, and you just want to treat the algorithm to make it fail. Okay, so I guess that's the model. And let's take a look at what's known in the literature and try to build some intuition. So I guess first of all, in the oblivious setting, which means adversary either sends all the queries in a single batch, or I mean, even if the algorithm and the adversary interacts sequentially, the next query the adversary sends is just independent of all the interaction history so far. So I guess if in the obvious adversary setting, it's very well known that with log Q over alpha squared samples, you can just answer all the queries very accurately within error alpha. This is just by Chernow plot. Once you have 1 over alpha squared samples, you can get very close answer. And once you invest a little bit more data points, your confidence increase very fast exponentially. So that's how you end up with log Q over alpha squared, which is cool, I guess, because this is independent of the domain size big N, and also it is logarithmic in the number of queries, so a very sample efficient algorithm. And I guess also computationally efficient, because to do this, you just take the empirical mean. And when we move on to the adaptive world, I guess there are two, I think there are two typical regimes of interest. First of all is the what I call an unbounded domain case, where we do not assume upper bound on the domain size big N. And in that case, it is known that in order to answer big Q queries, you need at least square root Q over alpha many samples, and it suffices to have square root Q over alpha squared many samples. And also realistically, as soon as your domain gets as large as 2 root Q, it's sufficient to carry out the lower bound attack. So, right. And in the bounded, there is also a bounded domain where we assume the big N is have an upper bound. So I guess just to develop some intuition, think about the case where your N is extremely small, let's say a constant. In that case, for example, if your N is 100 out of 1,000, then you can just invest a constant number of samples to just learn the distribution to a high accuracy. And then you can just answer whatever statistical queries you might want to answer. And I guess in the algorithm I just described, you still have a polynomial dependence on big N, but turns out even that is not necessary. So I guess in the differential price literature, there is a thing called private multiplicative weight algorithm. And if you combine that algorithm with the tight connection between differential price and adaptive data analysis, which is established by this Wesley, Nissan, Smith, Stanka, Stammer, and Wong paper, you get this square root log N times log Q over alpha Q as an upper bound. And I guess already in the original paper establishing the connection between privacy and generalization, it was observed that if you want to work within the framework of differential privacy, this is basically the best you can do. And yeah, so I guess this has also motivated a lot of research where one try to replace the differential privacy with weaker algorithmic stability notions to get more sample efficient adaptive data analysis algorithms. So I guess in this recent work, which I'm going to talk a little bit about next, we showed that basically lower bound of square root log N times log Q over alpha squared is an unconditional lower bound. So no matter how clever your algorithm is designed. And quantitatively, this can also be strengthened into a near tight lower bound of basically at 1 over 1 alpha under additional natural by sum of knowing assumption. We'll come to that later. And I should also say we are not the first to make this assumption. This is an idea first appeared in Smith, Stanka, Stammer, and Wong paper. All right, so that's, I guess, literature survey and results overview. And next, I guess let's try to do some math. So I guess in the rest of the talk, I'll try to give a gentle introduction to the fingerprinting codes and how people have applied it to the domain of adaptive data analysis. And then I'll say a little bit about our new ingredients and how it fits into the current framework. Okay, cool. So I guess let's start by talking a little bit about fingerprinting codes. So I guess this is a combinatorial. Okay, so this is a combinatorial object first proposed by Bono and Shaw in 1995, and its original motivation was for digital constant distribution against parity. And I guess here a probabilistic fingerprinting code is a probabilistic code book, which means itself is a random variable C. which is p by n. So I guess the number of rows is imagine the number of rows is the number of queries, and the number of columns is the number of users you want to defend against. So each user I will receive a column as a code word, and say that now there is a subset S of users. They collude and try to publish a pirate code word. So I guess visually what we want to say is, okay, I guess Zoom audience can really see the whiteboard. Anyway, so just visually imagine you have a subset of the columns are available to this subset of users, and they try to collude based on the available information and publish a pirate code word, also a column vector of SD. And so by tracing, we mean, so I guess fingerprinting code offers the following tracing attack, which says if you assume a minimum consistency condition between the output code word and the code book, the subset of code book available to the pirate users, then you can name at least one colluding party I in this subset S. And I guess assuming some kind of consistency condition between the output and the input is kind of natural, because again, code book is randomly generated. So from the subset of users' viewpoint, they cannot really infer too much about the columns not available to them.
So what is the goal of this pirate code word?
Oh, okay, cool. So I guess imagine you are, so the original motivation is something like follows. So imagine you are trying to publish a movie to different distributors, I guess YouTube, Netflix, yeah, etc. And then you don't want your movie to be freely available online. And the way you protect against this is maybe there are, yeah, you create the, I guess, critical things, where each critical thing you try to encode a binary bit. For example, say I'm filming a movie now, I can take this perspective or slightly tweak a little bit. So that's encoding a bit. And then if a subset of the users collude and try to publish a pirate movie, then if one thing is the same across all their copies, then I mean it's conceivable the output must be also the same. But maybe when they combine and compare their different copies, they might find something is off with a certain thing, but then they can be strategic and manipulate however they want. And the fingerprinting code just offers a construction where if you just insert the critical bits, and then what you can guarantee is whatever the strategy the users use, you can always name at least one pirate from this colluding party. It is clear.
So I'm still not clear on what this published CS still supposed to have what property? Presumably supposed to fool somebody or?
Oh, okay, cool. So I guess for now, let's think the property of C sub. So I guess by the minimum consistent condition, I just mean so think about a row. If every user receives the same bit on that row, then output on that coordinate must be also the same. So that's I guess that's really the only thing what we assume for fingerprinting codes.
I see. So this CS still is supposed to have some dependency on this C star, which you haven't proven yet, I think.
Yeah. Okay, so I guess I was I was a little bit vague here. So I guess the only requirement of the C sub S is for every I, if C okay, that's right. For every I in P, I guess if C sub I comma very J, let's say I comma J equals the same, then I guess you would like it to be the case that C2 J is also the same B. So that's the only requirement you require, and and the guarantee is you can name at least one I from the set S from the output. Yeah, sorry, I should be more careful here. So I guess, yeah, so construction of fingerprinting, optimal construction of fingerprinting codes is well known. So it is known that you can have such a construction with the number of rows as small as n squared. And I guess in next, we'll be talking a little bit about the connection between fingerprinting codes and adaptive data analysis. Yeah, so I guess why fingerprinting codes are useful for adaptive data analysis. First of all, let's assume the existence of FPC for now. And then, again, in this seminal paper by Hart and Bowman in 2014. So I guess the previous mentioned the Bork et al. Paper focused on the upper bound side. And this is really a lower bound paper. It works in this exactly same adaptive data analysis model, and its main result says if you try to answer n squared times, oops, sorry, should have been n times d. Let me just edit it very quickly. Yeah, so the lower bound paper says if answer n times d adaptive queries up to constant accuracy is hard or information theoretically impossible. And their target is kind of simple once you assume the existence of FPC. So let's consider the following construction. You have your ground truth distribution D uniform over a small domain of size too small n. And the algorithm receives a sample from this domain and just think of it as a subset S of size roughly n. Sorry, subset of 2n here. And then the adversary will do the following. It first draws any independent codebooks from the fingerprinting construction. And then it interacts with the algorithm for T adaptive epochs, let's say. And each epoch there will be D rounds of interaction, where each round the adversary looks at one row of the codebook. And for now, let's say the adversary only sends the C sub JS to the algorithm and queries for the average of, average of C sub J I, where I is over, I is uniform from S. So I guess I'm cheating actually quite a lot here because this is not the model of adaptive data analysis. In adaptive data analysis, you are supposed to send a truth table or a query, and the algorithm will evaluate that query for you. But here, the information that ever sends to the algorithm, I guess, even depend on the subset S, which is actually held by the algorithm. Yeah, but I guess this is actually very important, and we'll go back to this point very soon. But for now, let's just accept this cheating and move on. So what will happen now is that upon receiving all the responses for every row, if the adversary loses all the pieces information he has about these expectations, he can construct one CTUD. And from this CTUD, the adversary will be able to trace at least one user I from the set S. And then what you do is just you just remove the user I from the set S and proceed to the T+1 round. So I guess here we are assuming in the next round or epoch of the interaction, the adversary will be able to send C sub J, comma S subtract I to the algorithm, which again is still cheating, but we'll address that in the next slide. All right, so I guess after all these n rounds, it must be the case that all these data points are all compromised, or the adversary just learns all the exact subset. And that stage, what you can do is just you can craft a random query defined only over the remaining of the domain. Sorry, should really be 2n subtract S. I guess one way you can accomplish this is set Q sub S to be identically 0 and set Q sub Q of other things randomly. Then the algorithm cannot really evaluate the query accurately if they do not see the whole evaluation map.
Are you sending over each row J, like all through 1 through 8? Like all D rows?
Yeah, all D rows. Yeah. Thanks. Yeah. Okay, cool. So I guess this is the top, and So I guess here we have a total of n epochs, and every epoch we have d rounds of interaction of d queries. So this is the total of n times d queries, which combining the construction of FTC translates to n cubed, I guess. And I guess then just two remarks about this talk. First of all, how does adaptivity help in this process? So if you think about it, the only place where we use adaptivity is we will remove an exposed data point after every d queries. And this is kind of a limited adaptivity and seems wasteful. So why would you complete a full epoch and then start the talk? And I guess to address this, the follow-up paper by Stanka and Woman gave a more efficient talk where you can compromise a EDA algorithm with n squared rounds of interaction. And yeah, I mean, it has a lot of beautiful ideas here as well, but I mean, fundamentally, we are not really doing anything new on that front. So I guess we'll just skip that part for today. And I guess only knowing there is a polynomial, I mean, there is a targeting polynomial number of queries is already exciting enough, I guess. So I guess the in this paper or in this talk, we'll address another caveat of this talk. So I mean, if you believe in this talk, then it seems somewhat magical because you have a domain of really small size, 2 times n, to carry out the talk. But given the upper bound, given the available upper bound, which is polylogarithmic in domain size n number of queries, this is really impossible. So I guess this is the big catch we have mentioned in the last slide. The adversary is actually required to send the truth table of the full query, which includes evaluations to points not available to the algorithm. Then I guess what would happen is if your algorithm knew the ground truth is just uniform over 2 times n, if it also gets to see the truth table of the query map, then you can just evaluate the query pretending you have the distribution D. And then you can do that even without looking at your data points. So I guess, yeah, so I guess the solution to this caveat is, I guess one solution is you can augment this the domain to n times 0, 1 to the q. So intuitively, what you are doing here is you let each data point have a length q key, secret key, think of it as a one-time pad to encrypt its evaluations on all these q queries. And now I guess the rough idea is, right. Yeah, so I guess the idea is if the algorithm does not see an example of the form x, secret key, it has no access to the secret key, and therefore it cannot really evaluate the queries, all the q queries on the data point x. So I guess what that means is even if the algorithm knows marginally the distribution on the first part is uniform over n, if the algorithm does not have the knowledge of the second part, the 0, 1 to the q part, then it must receive samples from the distribution to learn the secret key and be able to evaluate the queries. So I guess if you know the idea and you spend, I guess, enough time, you'll just figure out how you want to implement the details, which I guess we'll skip for today. And
sorry, I have one question. Is there a way to do this attack without the distribution ruling?
Good. So I guess, in a sense, yes. I mean, in the upcoming attack, we are going to present. We are not working with uniform distribution. But as for this classical n squared attack, usually what people do is you set up the distribution to be uniform, at least over the first part, and then you are randomized to some stuff on the second part of the secret key parts. Okay, cool. So I guess, but however, this reduction cannot really work when the domain is of limited size. So I guess one thing you can still do is you make cryptographic assumptions, for example, existence of one-way functions. And then you can do a more efficient encryption scheme, which is already done in the in previous paper by, I guess, Hart and Allman and Stanka. But I guess here we are really interested in information theoretical aspect of the problem. So I guess we do not want to make crypto assumptions. Okay, so I guess which really comes to the not yet, but okay, let us take one step back and aim for something a little bit weaker. So I guess now if you think about what we are doing in the hard Oman attack, what we are doing is really as follows. So suppose you have a distribution over the domain, and now let's say you can prepare a queue, which is a batch of queue statistical queries, and you ask them in a single batch. And now suppose we have an algorithm that pulls a sample from the distribution, and it receives all the queries in a single batch and answers all of them. And in that case, a membership inference attack against the algorithm is just a procedure that it has the knowledge of the distribution D and all the query answers it wants through AQ. And it has no information about the sample S, which is kept secret to the algorithm. But nonetheless, it can learn a hypothesis edge such that, so I guess here actually is not a binary hypothesis, but pretend for the moment that it is. So what the hypothesis can do is, if you draw a random point from the distribution with high probability that hypothesis will label it as negative, whereas if you draw a point from the sample S with a decently high probability, actually will label it as positive. So that's a membership inference attack because by using the hypothesis, you can at least infer the membership of at least one data point in the sample S. And so if you think about what you are doing in the fingerprinting attack, we are really just doing this membership inference one at a time. And once you can infer the membership of all data points, the algorithm can just be, account. Okay, so so the message here is if we can design a membership inference attack, just visualize to this setting, we are usually very close to adaptive data analysis attack. So, and from this perspective, fingerprinting code is just one way to design MIAs. Okay, so I guess, yeah, so I guess now really I can talk about something new in our paper. So how do we design a membership inference attack? So think about this question, what aspects constitute a hard query family? So let's take a kind of a simple geometry viewpoint. So think about the query family Q as a set of endpoints in a two-dimensional Euclidean space. So what that means is, imagine you want to evaluate all these queries in a single batch. Then for every data point X in big N, you can write down the contribution of X to all the Q queries and think of it as a two-dimensional Euclidean vector. And from this perspective, query releasing for the set Q is nothing more than doing mean estimation or giving endpoints from the common set K, from the set K, approximate their average. And I guess from this viewpoint, it kind of explains very clearly why a small domain makes the problem easier. Because if your big N is small, then the set K consists of smaller number of points or vertices. That makes the from a geometry-wise, that makes the Q kind of a thin convex body, and which makes the mean estimation task easier. But these are all intuitions, and how do we want to prove lower bounds? Well, I guess we'll do a little bit of calculus, and which is inspired by previous works, I guess. So let's say you have a parameter theta, and you define a parameterized family of distributions, where d sub theta of k is going to be a distribution over k, where the probability you have to sample x sub j is proportional to the exponential of the inner product between theta and x sub j. So I guess when theta is all zero, this is the uniform distribution over the whole k. And when you move theta around, freely around in the Euclidean space, what we will do is, once you have a theta, you will put more favor on those points that are more aligned with the direction of theta. And then a natural conjecture to make here is, if you just happen to choose theta properly from appropriate region, and then you define your distribution to be d sub theta k, the problem is going to be hard. One highlight here is this construction here, theta doesn't need to have a product structure, but that's maybe too technical. Okay, so I guess why we should expand this too hard? Okay, cool. Yeah, I guess we'll do a local to global connection. So I guess suppose you have an algorithm that only operates a single data point just for simplicity. Then what would happen is if you look at the average behavior of the algorithm when you are on the distribution piece of data, and then imagine you move the theta a little bit to its neighborhood. So namely, let's take the derivative with respect to theta I. Then what would happen is you would get exactly the expectation of the inner product between E of x sub I and x sub I. So I guess after all, this is just due to the fact that if you have an exponential function e to the f and you take the derivative, what you get is f prime times e to the f. So e to the f is preserved, so which means you can still draw this x from the same distribution, and you get an f prime term, which squeezes out this desired xi minus expectation. And okay, so I guess popular definition calculus is the divergence of a multi-output function, which just sum over all direction I and derivative with respect to I and f sub I and x. So if you just do that on our function, what you will end up getting is just the inner product between the output of the algorithm, which is a, let me remind you, is a t-dimensional vector here, and the bias of the data point with respect to the average of the distribution. So this is a local viewpoint. It says that how fast your algorithm adapts to the change of theta is directly connected to how the output of the algorithm is correlated with its input. And okay, so for the purpose of privacy algorithm of lower bounds, a message here is private algorithm cannot really depend too strong on single point, but forget about it. Okay, so then let's take a global viewpoint where we say an accurate algorithm must adapt to data quickly. Here we just use the again a popular theorem from the calculus, the divergence theorem, which says the following. So let's imagine you have a closed, or maybe even compact, smooth, whatever good property you want it to have. Let's say you have such a region theta, and then you take the integral of the divergence of the algorithm over this region theta. And what that integral turns out to be is when you take a theta from the surface of the region, and you look at the inner product between the algorithm's behavior on the surface. I mean, inner product with the normal vector at that point. So I guess here the intuition is, oops. Sorry. What's going on here? Sorry, this is not really what I want. Yeah, so I guess the first term is what we want to understand, and the second term is something we can actually lower bound. I guess this is because imagine you have a surface, and you choose a theta at the surface, and when you define the distribution piece of data, you are favoring all these points from T that have a large inner product of the theta. So that means if your algorithm is going to be accurate, the output of the algorithm is also going to align very well with this direction. So that's how you can lower bound the right-hand side of the equation, and therefore lower bound the left-hand side. Okay, cool. So here we have a tension between privacy and accuracy, which said the accurate algorithm must adapt to the change of theta very quickly. And but quickly adapting to the change of theta means E of x must have a high correlation with its inputs. And this correlation is something you can take advantage of to design membership inference attacks. And all these intuitions are quantified by the correlation statistics, which looks at the output of the algorithm versus the bias of the data points. And you just analyze it from the, both the local and the global viewpoints, and properly assemble these two parts, you get what you get. And okay, let's just conclude by mentioning our construction. So we are essentially applying the framework to 3 different geometries or different constructions, and you glue them together to get the aligned lower bound. And all these 3 constructions, if you look into the literature, they're actually very popular and have been extensively studied before. We are just writing the correct lower bounds in our language, which makes things more convenient and make the whole proof go through. And okay, so the first geometry is, imagine you have a domain of size Q, and you have Q queries which form a Hadamard basis, or whatever nearly orthogonal query basis is fine. And so this recovers actually the Denour-Nissen reconstruction attack in a sense. So if you recall the Denour-Nissen reconstruction attack, the domain is of size n, and you have a less than 0.01 string as your private input. And then what the adversary do is it sends you a couple of random inner product queries. So you can easily convince yourself if you have n random inner product queries over 1 through n, they are going to be nearly orthogonal, with high probability. And yeah, so I guess this part is where we get the 1 over alpha squared lower bound essentially. And the second geometry is you have a small domain n, and you just ask all the possible 2 to the n counting queries over the domain n. And this is actually a convex body, a very high dimensional space, but at the same time, it's a very thin. It has only n vertices. So actually, it's even degenerate, I guess. And I guess this requires a folklore reconstruction, where you can find a reference from, for example, Woman and Wodan. So I guess here, we call this a reconstruction attack because imagine you have a distribution or a data set over 1 through n, and you are going to answer all the 2 to the n counting queries over your data set or your distribution. And what you can end up doing is you can just reconstruct your data set very accurately in L1 sense. So that's how you get log Q. And the third geometry is just the popular one-dimensional queries. So it's more convenient to write using the language of K. So the vertices are just going to be all the 2 to the D vertices of a Boolean hypercube. And this is just one-dimensionals. And this is where you get square root log n. And this is kind of dual to geometry 2 in a certain sense, right? Here you have many vertices, but a few queries. And here you have way too many queries, but only a few vertices. It looks superficially interesting, but yeah, we'll see. And if you just assemble these constructions, you can get the what we claimed before. Okay, just let me conclude by mentioning open problem. So I suppose our lower bound and the previous lower bound in the unbounded domain case can be upgraded to the correct lower bound. Namely, you can add 1 more alpha to the lower bound by making the following assumption. So the assumption says the algorithm's answers are required to be alpha close additively to both the population and the empirical sample. And I should say this assumption is satisfied by all the state-of-the-art algorithms, whether you are doing differential privacy, subsampling, or anything in between. However, it's not clear how essential this assumption is on the lower bound side. Or if you're an algorithm person, it's also interesting to ask how this assumption limits the possibility of algorithm design. And I guess science close this gap is a very important problem. And yeah, I'm happy to discuss more. And if you happen to already solve it, I'm happy to listen to the solution. All right, thank you.